All right, here we are. Another day, another lecture. Ready to move ever onward in our exploration of the wonderful statistical course that is Stat 512. So last week we continued, actually concluded our discussion of simple linear regression. Um, we talked about hypothesis tests for the slope and the y-intercept, although we observed that typically the slope is the only one that we're interested in testing. Um, you either understood what I was talking about or you spent the week productively going through that review material, communicating with me via email, perhaps checking in with some of our graduate assistants, and making sure that you understand that. If it's something that didn't click, you need to remedy that. It is not something that's going away. I am threatening you right now. Yes, that's right. I am threatening you. I'm threatening you right now that you can expect to see a lot of questions on exam one that are going to require you to use those tables effectively. You need to know how they work. You need to know how to use them. And if you don't, then I think you're going to be okay for this lecture. So don't let that deter you from keeping current. But at the same time, you need to be going back to that review material and or working with me to put together a plan to get you where you need to be. All right. So the last thing we talked about last week, you might recall, was this kind of not so excitingly phrased coefficient of determination, right? So remember from last class, at least in the context of what we were talking about, which was simple linear regression, right? Simple linear regression, 1x, 1y. The coefficient of determination, the r squared, is the measurement of the percent of the overall variability in y explained by its straight line relationship with x. This is it's going to be the important bridge that we need to move from that simpler framework into something that is admittedly more complex, but at the same time far more useful. The implications of this r squared, well, the implications are what? The implications are that we can look at the variability in y. We could look at the variability in some random phenomenon, say the weight of a bear, say the grade on a test, and we can say that that variability could actually be decomposed in different ways. It could be broken into these separate disjoint pieces. In particular, there's a part of it that's explained by its linear relationship with x, and the part of it that is not, right? The leftover, the remainder, the residual. Right? We saw that with the concluding example from last week. The concluding example from last week, recall, x was the amount of time you spend studying on an exam, one that may or may not involve, well, it definitely will involve lots of questions about using a t-table, and y, the grade that you get on that exam. And we said the correlation was 0.7. That means that the coefficient of determination was 49%. So 49% of the variation, right, is explained by the amount of time you spent studying. That was one piece. And the second piece was, right, that 51% that is still remaining, right? That is not explained by that relationship. We can represent this concept algebraically, right? And that's the formula that does so right there. So if we look at the left-hand side of the equality, what does that look like to us? Exactly. It looks like the numerator of the sample variance, right? Basic Stats 101, the sample variance S squared, right, is mathematically defined as that quantity on the left divided by n minus 1, right? That n minus 1 is just a scaling factor, right? All the magic is happening upstairs. It's happening in that numerator. So that numerator is essentially a measurement of the variability in y. And what we're seeing from equality is that it could be broken into these two different pieces, these two different sums. It's not particularly hard to actually prove this. I just don't know that I believe it's worth our time. It's really just a lot of kind of like it's a lot of painful, painstaking, tedious kind of just algebra. You expand out those squares and combine some terms, cancel some terms, and you can prove that that right-hand side eventually sort of simplifies into the left-hand side. I don't know that that's a worthwhile exercise for us. I want us to instead just focus on this idea that that variability in y being represented by the left-hand side of our equation could be broken into those two pieces. The rightmost piece, right? We've seen that rightmost piece before. That rightmost piece is y minus y hat, right? That's sort of observed minus expected. That's our residual. And of course, we're squaring it and we're summing it up. That's the sum of the squared residuals, although we called that SSE, right? Sum of squared errors, because the residuals are also thought of as the errors. That's the remaining variability. That's the variability that's left over after fitting our regression model, right? Unfortunately, in most cases, our regression model does not predict y perfectly. There's still some remaining error. So that's that SSE. That's the error left over. And so by default, that remaining term, right, that y hat minus y bar term has to be the amount of variability that's sort of soaked up, the amount of variability that ends up being explained, that ends up being accounted for by our regression model. We call that piece, or abbreviate that piece, SSR, sum of squares regression. The amount of the variability in y explained by our regression model. That's the SSR. The other piece is the amount of the variability left over or unexplained by our regression model. Right? And then at the bottom of the slide, you can see that I summarize everything that I just said in terms of words. The total unexplained variability in y equals the variation due to its regression relationship with x, and then the remaining unexplained residual variation. We can take that and come up with another following math fact. Again, I'm not going to spend time to prove it, although in this case it's not particularly challenging to prove. Again, it's just more tedious algebra. We can take that those formulas from the previous slide, SSY minus SSE over SSY, which is equivalent to SSR over SSY. You should be able to see that equivalency fairly easily, right? Because SSE plus SSR equals SSY. And then take that formula for correlation that we had way back in our first week, square that formula, you can show that they're algebraically equivalent. Which means that, right, you square the correlation, R squared. Remember, that's our coefficient of determination. The coefficient of determination could be shown to be algebraically equivalent to SSR over SSY. Now, what is SSR over SSY? Well, SSY is the amount of variability in y, and SSR is the amount of that variability explained by the regression model. So what do we now see quite clearly? It was something that seemed a little bit magical last week, but now is actually quite transparent to us. And that is that R squared is in fact the percent of the variability in y explained by its regression relationship with x. So what? Well, we care about this because it gives us another tool to help determine when a given model explains a, quote, significant portion of the variability in y. And you might say to me, if you're so inclined, you might say to me, well, hold on a second, Professor McClintock. Why? Why do I need a third way to do something that I already know how to do? If I want to test whether there's a relationship between X and Y, well, I already learned how to do a hypothesis test of slope. That does it. And on top of that, you taught me how to do a hypothesis test for whether or not the correlation is 0 or not 0. That's a second way of determining whether there's a relationship between X and Y. Do I really need a third? And what's next week going to be? A fourth way to do something I already know how to do, and a fifth way to do something I already know how to do? Why did I spend all this tuition money just to learn the same thing over and over and over again? And all right, fair enough. Fair criticism. But it's important to learn this, because what we will see is that those first two methods that we talked about last week are very specific to simple linear regression. They work well in that context, but they do not extend beyond it. This third method that we're talking about right now, this method of decomposing variability that we're going to develop right now, is important because it does generalize. We already motivated the idea that 1x is not enough for any type of interesting real life example, right? Any interesting variable y is probably a function of many variables, and that's what we want to be able to model. That's what we want to be able to handle. And we will see that this method that we're doing now will extend to the situation where we're working with multiple variables, whereas the two methods that we learned last week do not. And that's why this method is important enough to spend an entire week, which is, yeah, that's what we're going to do, an entire week talking about. Now, that's the big idea. But what's the problem? Well, the problem is this, right? It should be intuitive to us. It should be intuitive to us. And if it's not, then you should reach out to me. Or at least you should kind of find a nice little quiet COVID-free corner of your bedroom and meditate upon it. It should be intuitive that large values of R squared are indicative of a model that explains a significant amount of the variation in y, right? Because what's R squared? R squared is the percent of the variability in y explained by x. If most of the variability in y is explained by x, i.e. we have a large R squared, well, that means that x is extremely important, right? So R squared becomes like sort of this intuitive metric for us to use. R squared is always between 0 and 1. The closer it is to 1, the stronger the evidence that x is useful in predicting y, that x explains a significant amount of the variation in y. The problem, though, is what? The problem is, right, and this is, we know this from all the other statistics that we've studied thus far, is you run into this question is like, okay, how large is large enough? Is an R squared of 10% large enough that I say, okay, x is significant? Is an R squared of 20% large enough? Is an R squared of 30% large enough? Like, how do I come up with like a threshold? And of course, conventional statistics does this how? Conventional statistics does this through a p-value. But a p-value is what? A p-value is a probability. The p in p-value stands for probability. And to generate probabilities, what do we need? Exactly. We need to know distribution functions, right? Every p-value that we calculate is a byproduct of a distribution function, right? It's a byproduct of a normal distribution. It's a byproduct of a t-distribution. That's what we talked about last week, right? The probabilities are generated from a distribution function. That's the only way to do it. Can't generate a probability out of midair. Trust me, I've tried. However, so the problem is what? The problem is that R squared is this intuitive metric, but R squared does not have a sort of consistent, provable distribution function. And that means that we can't generate a p-value off of R squared. So what do? Do we give up? No. Statisticians never give up. What we do instead is we persevere. right? We push on. We take the R squared, which will make a nice like heart of a test statistic, and then we just tweak it in some way. We tweak it, we massage it mathematically in such a way that we can prove that we can derive its distribution function. And then, once we have the distribution function, the p-values just kind of fall in place, don't they? So, right, the question now becomes, how do we do that? Well, the solution is this. Instead of looking at the ratio of SSR to SSY, oh man, what is that again? Ah, geez. Sorry, I didn't get a lot of sleep last night. What's SSR over SSY? That's right. It's the R squared, right? So instead of looking at the R squared, the intuitive metric, we look at something a little bit less intuitive. It feels like a little bit kind of like unnecessarily complex, but there is, I promise you, there is necessity to the complexity. Instead, we look at the ratio of MSR to MSE. So instead of the sum of squared regression, we look at the mean square regression. Instead of looking at the sum of squares of y, we look at the mean squared error. The mean squared error we actually looked at. We looked at that last week, remember? And that was defined as the SSE over n minus 2. Although again, it should be emphasized that that formula is actually only true in the case of simple linear regression. We'll see it changes a little bit when we move to multivariate regression, more than 1x. Similarly, MSR is like SSR divided by 1, right? And I know you look at that and you're like, what the kutha? Like, what is, divide by 1? That's actually not doing anything, right? Isn't that how we as mathematicians, as statisticians, maybe we trick our parents, maybe we trick our spouses, like our spouses or our parents are like, oh man, I need you to take out the garbage, right? I need you to like clean the house. I need you to do something. And you're like, oh man, I'd really love to, but I'm dividing by 1 right now. And then it sounds like you're doing something like pretty mathematical, like, oh man, okay, they're dividing by 1. I don't want to interrupt that. But I mean, you're not lying, right? You're being honest. Dividing by 1 is not really doing anything, is it? And maybe that's exactly what you're doing, is you're sitting around doing nothing. So you might say, like, why? Why am I dividing by 1? Well, again, this formula we're looking at now is just for simple linear regression. We will see that these formulas change when we go to multivariate regression, okay? Now, this thing feels a little less intuitive, right? We've changed in a couple ways. We've gone from sum of squares to mean squares. We've also changed that denominator, right? It's no longer the total variability. You're no longer looking at like sort of a ratio of explained variability to total variability. You're now looking at a ratio of explained variability to unexplained variability, right? But that's still analogous, isn't it? Can we see that? Can we see that it's still kind of conceptually the same, right? If you look at the ratio of explained variability to total variability, the larger it is, the more explained variability there is. Similarly, if you look at the ratio of explained variability to unexplained variability, it still has that same sort of relationship. That is, the larger that ratio is, the more of the total variability is being explained by a regression model. Agreed? And so these two quantities, these two ratios are analogous. They're analogous in the sense that larger values are indicative of stronger evidence that there is in fact a relationship between x and y. All right. And although this new quantity feels a little more unintuitive, for example, it's not like a percent of variability, which is like a very nice property of R squared. We've lost that property. We've kind of thrown it to the wind. it does have a new property, and that new property is that we can mathematically prove the distribution of this new quantity, MSR over MSE. And so what we're going to do is we're going to spend a few slides, for better or for worse, kind of talking a little bit about kind of this MSR over MSE and what its distribution ends up being. So here's a math fact. It's the type of thing that you'll see in Stat 506. In fact, I think actually typically, if your 506 is being taught right now by the great Professor Gallup, I believe that it kind of coolly coordinates, in that, right, as you're learning this in 512, you're actually learning this particular math fact in 506. So again, I sometimes waffle back and forth about the value of these couple slides, but I do think it's nice because it takes that very theoretical 506 class, which sometimes can feel a little disconnected from the application of statistics, and at least try to show us, like, no, that's actually not the case. It's actually extremely important in terms of kind of everything that we're doing in this core Stat 512 class. Now, I know that 506 is not a prerequisite for Stat 512. So if you are one of those students, and there's always a few, if you are one of those students that's not taking 506, that has not taken 505, don't worry about it. Feel free to kind of tune out the next couple slides, or even better yet, try your best to understand as much of them as you can. And if you don't understand all of it, that's fine. You can let yourself off the hook. I promise at the end of these next 3 or 4 slides, I will tell you the punchline. I will tell you the takeaway. I will tell you of all that stuff, this is what you need to know. Now, let's go back to 506. This is a math fact. You could prove it if this was a theorem proof kind of class. Consider a simple random sample from a normal distribution. We all know what a normal distribution is, right? Even if we've not taken 505. That's just basic stats 101. My kids learned that in kindergarten. With a mean of mu and some standard deviation sigma, then math fact, n minus 1 times s squared over sigma squared, that particular ratio, which is equivalent to, right, that summation over sigma squared, right? Because s squared times n minus 1 is just basically stripping away the denominator of the variance. That quantity follows what's referred to as a chi-squared distribution. Now, chi-squared distribution is not super important for our class, other than being an intermediary step for where we're going. So I'm not going to get too heavily into a chi-squared distribution. But very similar to a t-distribution, it has something referred to as degrees of freedom, right? And the degrees of freedom, they're a technical term, but all they are is just some numerical characteristic that controls the shape of that distribution. Slightly different degrees of freedom lead to slightly different shapes in terms of our chi-squared distribution. Now, last week, we talked about how the MSE, right, the mean squared error, is a best guess for the true but unknown common variance, hypothesized common variance, sigma squared. It's also true, right, this is sort of the analogous fact, the 512 equivalent of the fact from the previous slide, that the MSE times n minus 2 divided by sigma squared follows a chi-squared distribution with n minus 2 degrees of freedom. So the MSE times n minus 2 divided by sigma squared, we know its distribution. It's a chi-squared. Now, it turns out that the MSR also estimates that same variance, but only under the condition that our null hypothesis, so I know I haven't formally stated our null and alternative, but we're still working under the same framework as last week. And the null and alternative from last week were, null hypothesis is that the slope is equal to 0. Alternative hypothesis is that the slope is something other than 0. So when the null hypothesis is true, MSR estimates the same variance. If the null hypothesis is not true, the MSR overestimates the variance. Also, under the null hypothesis, MSR over sigma squared follows a chi-square distribution with 1 degree of freedom, right? Maybe we should have written that as MSR times 1 if we wanted to fool our parents. One last math fact is that the MSR and the MSE are independent of one another. That's important because ultimately what we want to do is we want to use this final math fact right here. And this final math fact says that if we have two random variables, x and y, both of which are chi-squared, x has a degrees of freedom, y has b degrees of freedom. And, this is important, and x and y are independent, then x divided by its degrees of freedom over y divided by its degrees of freedom could be proven mathematically to follow something called an F distribution. The F distribution is going to be important to us. We are going to use the F distribution probably every day of class from this point on. The F distribution is sort of the pivotal distribution for multivariate regression. That is, the ratio of two independent chi-squared distributions divided by their degrees of freedom follows something called an F distribution. And so we could probably see where we're going with this, right? We can see the kind of key takeaway, the main point. That is that this MSR over MSE is going to take advantage of all these different math facts and allow us to see that that ratio of MSR over MSE follows an F distribution. Yeah. That means that we could use the MSR over MSE as a test statistic because, right, all those previous math facts imply that it follows an F distribution. And since we know the distribution, we can use that distribution to generate p-values. Pretty cool, right? I should say, I think I forgot to emphasize in that previous slide that the F distribution is like a little bit unique, at least relative to what we've maybe been exposed to thus far. A little bit unique in the sense that it actually has 2 degrees of freedom. It has something called a numerator degree of freedom and something called a denominator degree of freedom. And that makes sense, right? Because the F statistic is what we sometimes call like a man-made statistic. It doesn't really occur in nature. It's kind of like what happens when we as like statisticians take some random variables that occur in nature and you know, create functions and ratios with them. That's what we're doing now. We're sort of like building the sort of, maybe it's like F for Frankenstein, right? Maybe the F distribution is a sort of like Frankenstein monster that we've kind of built piecemeal from all these different quantities and all these different theorems. But hey, whatever gets the job done. So we have a numerator degrees of freedom and denominator. In that previous slide, I stated it very generally. So the numerator degrees of freedom were A and the denominator were B. But in this example right here, we're looking at MSR over MSE. We've already implied that the degrees of freedom for the MSR are 1. And we've already implied that the degrees of freedom for the MSE are n minus 2, right? So our degrees of freedom, the numerator degrees of freedom are going to be 1. The denominator are going to be n minus 2, right? So the key takeaway is the quantity MSR over MSE is our test statistic. Larger values of that ratio provide stronger evidence that we should reject the null hypothesis, that in fact there is a relationship between X and Y. And this ratio follows an F distribution with 1 degree of freedom in the numerator, n minus 2 degrees of freedom in the denominator. So, what is this F distribution? It's a little different than what we've talked about in terms of previous distributions, right? The ones that we've kind of focused on in our review lecture, at least, is the normal distribution and the t distribution. The normal distribution and the t distribution are both bell-shaped symmetric distributions centered at 0. The F distribution is quite a bit different. The F distribution only takes values from 0 to infinity, and because of that, it has what's called a right skew. And that third bullet point I've already mentioned a few times during this week's lecture. Larger values of this test statistic, right? The farther out we go in terms of this F distribution, the stronger the evidence that we should reject the null hypothesis. Okay. Oh, for the record, the chi-square distribution actually looks quite a bit like this. Again, not a big part of our class, but worth noting. The chi-square distribution is kind of similar to the F distribution in the sense that it's this kind of skewed right distribution that goes from 0 to infinity. So here's the shape of an F distribution for a few different parameters. So you get a sense of how, right, there's 2 parameters that control its shape. There's a numerator degree of freedom and a denominator degree of freedom. And so you can see it changes it, but I mean, all 4 of those have that same sort of basic right skew shape, right? And that's kind of what we're looking at. So, as I've already said, it's important to me that you understand how to use these tables, even though, right, at the end of the day, we'll be having SAS or R or some other statistical package do it for us. I think that understanding how the tables work is an important step for us building like an actual sort of fundamental understanding of what's happening, rather than just kind of being like a little bit like statistical monkeys and just kind of sort of blindly repeating a process that we don't really understand like what that process is or how that process works. So the tables are actually, they're ultimately simpler than the t-table. So if you struggled a little bit with the t-table, I think you'll find using the f-table easier. However, there are like 7 of these tables that we have to work with. The tables are set up in such a way. So if you go to if you have the 5th edition textbook, you can open your textbook and look at these pages, page 921 to 927. For those of you that maybe don't have the textbook, I have scanned a copy of the tables. The scanned copy unfortunately comes from an earlier edition of the textbook. So I think the page numbers on the scanned copies are like 800 something. And I have posted that scanned copy on D2L. So if you don't have the textbook, you could pause this and go print those tables out so you can refer to them. You are going to need to refer to the table as I work through these slides. The way the tables work is they help us find critical values for different alpha levels. Now, the critical value depends on two different things. It depends on, well, it depends on one thing, the shape of the distribution, but the shape of the distribution depends on two things, the numerator degrees of freedom and the denominator degrees of freedom. And so the first thing that we have to do is we have to pick the correct table. The correct table depends upon what alpha level we're interested in. Often we're interested in an alpha level of 0.05, but I'll teach us how to do it for other alpha levels. Now we're going to take a quick little break here. It's the nice part about working at home. Sometimes your wife walks past you. You can give her a smooch in the middle of your lecture. I don't normally get to do that in the classroom. All right, back from smooching. Our alpha level is 0.05. So if you look at these different tables, I'm kind of looking at them right now. Should have asked my wife to turn the light on in this room. It's a little gloomy in here. All right, so the very first table, page 921, if you look at the very top, it says upper 25th percent point of the F distribution. So that's like an alpha of 0.25. We don't want that. The next one says 10%. That's like an alpha of 0.10. We don't want that. So the third table, page 923, says upper 5%. That means that's the alpha of 0.05. So that means that, right, we gotta do the degrees of freedom now. So if we look at our table, it says that the rows correspond to denominator degrees of freedom. The columns correspond to numerator degrees of freedom. So we've got 1 degree of freedom in the numerator, and we go down to 36 degrees of freedom in the denominator. And you should hopefully be able to see that that gives us 4.11. So what does that mean? It means that the probability that an F distribution is greater than or equal to 4.11 is equal to 5%. Right? Any test statistic that's more than 4.11 is going to have a p-value smaller than 0.05. So essentially it's saying if our test statistic is larger than 4.11, this is kind of like a rejection region approach. If our test statistic is more than 4.11, then our p-value is going to be smaller than 0.05. Because our p-value is going to be the probability of seeing something as large or larger than our test statistic. Okay. So what about if we had an alpha of 10%, 0.10, 5 degrees of freedom in the numerator, 60 degrees of freedom in the denominator? What would that look like? Well, we sort of got to go back a page. So now I'm looking at 922, page 922. In the upper left-hand corner, it says the 10% point. 5 degrees of freedom in the numerator, so that's the column. 60 in the denominator. I'm getting old. I think that's a 1.95. I wouldn't swear it's not a 1.96, but I'm pretty sure it's 1.95. And yeah, so that's the answer that we have there. It means that, right, for an F distribution with 5 degrees of freedom in the numerator, 60 degrees of freedom in the denominator, the probability of seeing something 1.95 or larger is equal to 10%. Now, again, I expect you to use the tables, but we can also use SAS to find the probabilities. Once you've proven to me that you've perfected using the tables, once you become an advanced Stat 512 student, it'll be perfectly acceptable to do things like this. We could find probabilities as well as percentiles, right? So that first question is trying to find a probability, right? What's the probability of F distribution with 5 and 40 degrees of freedom being more than 2.9? That would be like finding the p-value for a test statistic that's 2.9, you know, if that distribution had those degrees of freedom. So step one, and that is something that we should hopefully understand. Step one is essentially finding the p-value. Question two is essentially asking us for the critical value for a 0.05% significance test, for a significance test or hypothesis test using an alpha of 0.05. Right? Again, these are things that I kind of expect you to be comfortable with, just based off an understanding of kind of like that basic statistics. And again, I think some of you fall in that camp, but I could also guarantee some of you don't. And that's fine. Again, it happens. There's a decent chunk in every class that, I mean, it's not easy. If this was easy, everyone would be doing it, because trust me, being a statistician is the best job in the world. So think about it, meditate on it, read through the book, touch base with me, touch base with the graduate assistants, right? You need to get there. You need to hopefully understand, this is a nice concept check, that question one is basically solving for a p-value. Question two is essentially solving for a critical value. So we find probabilities with the prob-f function in SAS. We find percentiles with the f-inverse function. There's other functions as well, but these are some of the functions that will work. So the prob-f function actually gives all the area to the left. So you got to give it the actual thing you want the probability of. So here we want the probability of 2.9, then the numerator degrees of freedom, and the denominator degrees of freedom. So the prob-f alone is actually the probability of being less than or equal to 2.9. Since we want the probability of being greater than that, we would do 1 minus it. F inverse, right, finds the value such that the first input is to the left of it. So our question said we want the value such that 5% is to the right. 5% to the right of this critical value means 95% to the left. So that's why we put the 0.95 in there, and then again the degrees of freedom. And so run the code yourself and verify that the answer to the first problem is right about 2.5%. The answer to the second problem is about 2.5. All right. And then for those of you that are inclined towards R, it's actually, I think, easier to get these things in R, just the way that R works as a command line language. You can just type that and hit enter, rather than having to sort of create this kind of weird data set and then do a proc print to look at what's inside of it. All right. So let's sort of step away from this forest and smell some trees. Yeah, Christmas trees smell so nice, don't they? Back to our bears, right? Back to our beloved, much ballyhooed bear data set. All of the information that we've just talked about is very cleverly summarized by something called an ANOVA table. So ANOVA is just an acronym for analysis of variance, analysis of variance. The ANOVA table kind of works like this, right? So you have these three different pieces. That's what we started this lecture talking about. You have your SSR, you have your SSE, you have your SSY. Each of these pieces have their degrees of freedom, right? We talked about that, right? The degree of freedom for SSR was 1. The degree of freedom for the SSE was n-2. And then the degrees of freedom for SSY are n-1. Now, if you do SSR divided by its degree of freedom, right, you get the MSR. If you do the SSE divided by its degrees of freedom, n-2, you get that MSE. Pretty cool, right? Notice also that, right, the way that our columns work, SSR plus SSE should equal SSY. Same with the degrees of freedom. 1 plus n-2 equals n-1. So we get our MSR or MSE, and then we have to create our test statistic. Our test statistic is the MSR divided by MSE. That gives us our F statistic. And then finally we get our p-value. Our p-value is the probability of seeing something as large as our test statistic or larger. So now, right, this is our output. We actually saw this output, just proc reg output. We saw this output from last week. It's just we focused on the bottom part, those parameter estimates, and kind of ignored the top part where it says analysis of variance. But that's essentially the ANOVA table, right? So we should be able to now see where all those numbers are coming from, right? Remember, 99 bears. So that corrected total is 99 minus 1, so 98. And the other one is 99 minus 2. The other degree of freedom is 1. For simple linear regression, it's always 1. So that first number, that 11114241, that's our SSR. Beneath it is our SSE. Again, I encourage you to do this rather than take my word for it, right? We learn by doing much more so than learning, right? Plug those numbers into a calculator. Do that 11114241 plus 132338 and see that it in fact does equal 1246579, whatever that is, right? That those two pieces, SSR plus SSE, does in fact equal SSY. Now, of course, that 1114241 divided by 1 is the same number, didn't change it. The 132338 divided by 97, it's close to dividing it by 100, right? Which so kind of goes from 132338 to almost like 13233. Or sorry, 1323 dividing by 100, not 10. So again, I encourage you, pull a calculator out, verify those numbers. It's how you learn it and remember it. Start studying for your test early. Then our F statistic, right? Again, verify 1114241 divided by 1364.30833. Do that division and see that you do in fact get 816.71. And then if you really want to kind of make sure you learn this stuff, go into SAS, use those functions that I showed you in SAS or in R, and calculate the probability in F distribution with 1 degree of freedom in the numerator, 97 degrees of freedom in the denominator, is greater than or equal to 816, and see that in fact that probability, which is our p-value, is immeasurably small. Probably far less than 0.0001. Also, right, we could look at some of that other stuff, in particular the R squared, right? So the R squared is 0.8938. So that means that, right, 89% of the variability in a bear's weight is explained by its net girth. You could also verify that if you do 1114241 divided by 1246579. Again, I encourage you, get your calculator out, put it in. That's how we calculated R squared, right? R squared, remember, was SSR over SSY. So do that division yourself and see that it in fact does equal 0.8938. Start to get a feel for how this kind of beautiful table all fits together. I forgot to harp on our déjà vu. So that p-value of less than 0.0001 was the same as the p-value for the slope, right? That we did last class. So remember, we're doing F tests now. We learned how to test the significance of slope with a t-test last week. In both cases, the p-values showed up by SAS as being less than 0.0001. it actually turns out that if we measured both those p-values precise enough to have the exact answer, the exact answers would be the same. Now, this is only true in simple linear regression. That f-test and t-test are always going to be the same in the context of simple linear regression. As we start adding more x's, we're gonna lose this equality. But in the simpler setting, they're always the same. And that's in part because of this kind of interesting final math fact of the lecture. And that is, we can sort of prove mathematically that if you square a t-distribution, the Greek letter nu looks a lot like the English letter v. If you square a t-statistic, you get an f statistic with 1 degree of freedom in the numerator and the same number of degrees, that v number of degrees of freedom in the denominator. So I can't scroll back to the previous slide without erasing everything I've just said, but I encourage you to go back to that output, look at the test statistic for our t-test, square that thing, and see that it ends up equaling the test statistic for our f1. I actually think I remember that the t-statistic, if I remember correctly, wasn't it like 28.58? So yeah, square 28.58 and see that you do in fact end up with whatever it was, 816 something. All right. Aha, there it is. That is yeah, that shows it. So our f statistic was 816.71, which is equal to our t statistic 28.58 squared, as promised. So this wraps up our discussion of the overall f-test, sometimes called the omnibus f-test. We'll talk a little bit more about why it's called that in the second half of this lecture. Wraps up our discussion of ANOVA tables. So we're at a nice natural breaking point if you want to kind of pause this video, take a break, take a breather, and then come back to it. We'll start the second half of this week's lecture, which starts to finally move us from simple linear regression to multiple linear regression, from 1x to more than 1x. All right, welcome back from your break. Hopefully you took the opportunity to smooch or hug or brighten the day of a loved one of your own. And now that you've done so, let's go ahead and wrap up this cute little beast. So moving on to chapter 8, right? We're finally ready to transition from simple linear regression, 1x, to multiple linear regression, any number of x's. Right? So now we're talking about some arbitrary number k. Could be anything. K could be 1,000,000. Independent variables that we want to put into our regression model, right? We've kind of already motivated that this is something that might be useful to us. And so now we're going to finally learn how to actually go about it and do it. So we could see what the regression equation actually would end up looking like, right? Y sub I, the weight of the ith bear. We still have this y-intercept, and then we have, right, a coefficient for variable 1, and a coefficient for variable 2, and a coefficient, right, for variable 3, and on and on and on until a coefficient for variable k. Now, even with all these variables in our model, it's still unlikely that it's going to be perfectly predictive. That is, it's going to predict perfectly every time. So on top of everything, we also have to add that error term, that e term. So in terms of comparing, right, multiple regression versus simple regression, right, this is, I think, obviously much more realistic and much more useful. However, right, that realism, that utility does come at a cost. Things become much harder to visualize, right? The scatter plots that we've been able to use to kind of help springboard our understanding of how regression works those scatter plots only work, a two-dimensional scatter plot only works with a single x. In theory, you could do a three-dimensional scatter plot with two x's, but they're much more difficult to create. I mean, I certainly can't do it by hand. And they're also, I think, a little bit harder for us to visualize. And then, of course, when you get to three x's, you know, now we're in like four-dimensional space. So, right, most of us don't live in that particular world unless you're some sort of time-traveling Tralfamadorian. You know, you're like me. You're stuck with three dimensions. They become a little bit harder to interpret. We'll talk about that in a few slides. And as we'll see through the remainder of the course, a lot of effort becomes necessary in terms of trying to figure out what is like a best model, right? So I mean, the problem we run into is like maybe we have like 20 variables. Maybe some of those variables are useful, maybe some of those variables aren't useful, right? So sort of the challenge that lies before us is that we need to somehow go through these 20 variables and figure out, right, well, which ones are good, which ones are bad, which ones are the best, which ones are maybe less than best. That's much more than we could tackle in this lecture this week. In fact, it's really going to take us almost the entire semester to be able to handle, right, a problem that big, but we're going to start laying the groundwork for that right now. Now, multiple linear regression also has associated with it some assumptions, right? How well this regression modeling is going to work is going to depend heavily on how well those assumptions are met. It turns out, right, the assumptions are same as before. That's actually going to be the running theme for the remainder of this lecture. Same as before, same as before, same as before, right? We've really already done the heavy lifting in those first 2 weeks. We'll see that much of what we've talked about extends pretty easily to multiple linear regression. So there they are, 1, 2, 3, 4. Right, I always encourage you to print these PowerPoints before you listen to the videos. So ideally you have this sitting on a piece of paper in front of you right now with a pen, maybe a pencil. I'm not going to tell them to you. You can go back to the slides from last week, maybe 2 weeks back, and write them down yourself. Ideally, you have them memorized and you don't need to go back. But if for some reason they're not memorized, you need to stop this video, go back, and write them down. You need to learn them. You need to love them, right? Remember, those 4 assumptions are all in terms of E. So we still have an E in our equation, and it still works just like it did before. Adding the extra x's doesn't really impact what's going on with that error term E. So, right, the basic process is we still go about, we generate our best guesses. These are statistics for the unknown values beta naught, beta 1, all the way to beta k by finding the estimates beta naught hat, beta 1 hat, beta k hat that minimize that sum of squared errors, right? So we're still building an equation. Right? We have 20 variables, but we're still using those 20 variables to just come up with a predicted weight for the bear. So we can still do things like compare the actual weight of the bear to the y hat, the predicted weight of the bear using all 20 variables. We want those numbers to be as close as possible. Right? Sometimes our best guess is above the answer, sometimes it's below the answer, which means sometimes we have positive numbers and negative numbers. We square it to prevent those from canceling. And then we just sort of aggregate it. Sum of squared errors. What was the theme of this lecture? Same as before. And that builds us a prediction equation. Y hat is equal to beta naught hat plus beta 1 hat x1 plus beta 2 hat x2, and so on. Right? And so again, like the geometric intuition, right? You could try to maybe imagine like if k equals 2, this is kind of like this is like working in like a 3-dimensional space. So I mean, look at the floor of the room that you're in, right? one wall of that room, like along the bottom part of that wall, you might think of as like your x1, and then you got the perpendicular wall that becomes like your x2. So any point on the floor, right? Any point on your floor is some combination of x1, x2. And then you could think of what? You could think of your y variable as like being like how far off the ground it is or isn't, right? So you really kind of have like your observations are these little points floating in three-dimensional space. And instead of fitting a line, we're essentially fitting a plane. So you imagine like this big plank of wood that you're kind of trying to orient in such a way that it's as close to these floating points as it could possibly be. When k equals 3, right, we don't even have the ability to try to use our imagination anymore. Nonetheless, right, all the mathematics still translates over. We still have an ANOVA table. Works largely the same way. One of the very few changes is in the degrees of freedom. So if n is the number of observations, right, n's our sample size, and k is the number of independent variables, right, the number of x's, then the degrees of freedom for our regression is k. The degrees of freedom for the error are n minus k minus 1. And then the total degrees of freedom, the degrees of freedom for the SSY are still n minus 1. So if we stop for a second, do we see how simple linear regression is like a special case of this? Right? If we're doing simple linear regression, that k is 1. So that gives us 1 degree of freedom in the numerator, just like we talked about earlier in this lecture. And n minus 1, which is n minus 2 degrees of freedom in the denominator, which is just like we talked about earlier in this lecture. This is another part that's a bit different, perhaps maybe the most different part, and that is how we set up the hypotheses that the overall f-test of the ANOVA table is ultimately testing. So the overall f-test is testing that beta 1 equals 0 and beta 2 equals 0 and beta k equals 0, that all of the coefficients are equal to 0, which of course would zero out all the x's. It would basically mean that none of those x's belong in our equation. The alternative is the negation of that, and that is, right, for the null hypothesis not to be true, all we need is at least one, maybe more, but just at least one of those coefficients to be something other than 0. Which is basically saying at least one of our variables is useful in the model. All right. I think I summarized that in words at the bottom of the slide. Let's see here. The null hypothesis is that none of the variables are useful in predicting y. Yeah. The alternative is that at least one is useful. That's why we often call this the overall or omnibus f-test. The R squared is still defined as SSR over SSY. It's still interpreted as a proportion. It's essentially, right, still really the proportion of the variability in Y explained by our now larger, more complex regression model. Larger values of R squared still indicate a better model. And this still has an interpretation relative to correlation. We'll talk about this kind of idea of like a generalized correlation in chapter 10, which I think is going to be 2 weeks from now. And the interpretation of the slopes is a little bit different. We interpret, right, either the theoretical slope or the best guess for that thing as the amount we expect y to increase or decrease after a 1 unit change in x. And then here's like this important little disclaimer, this important caveat. You don't put it on a homework, you don't put this disclaimer on a test, you lose points. We'll see in a little bit why it's so important. After all other variables are held constant. We could still use this equation to make predictions. We just plug in all of the x values of interest into the least squares regression equation, right? So if we wanted to predict the weight of a 20-year-old bear that has a neck girth of 15 inches, we just plug in 15 and 20. Speaking of bears, what if we were interested in whether or not age and length, so now we're working with two variables, our k equals 2, are useful in a larger model used to predict the weight of a bear? The SAS code, very, very easy. We still use proc-reg. We still use the model statement. You could put as many x variables as you want on the right-hand side of that equation. It's that easy. The output looks very similar, doesn't it? Let's look at the ANOVA table, right? 2 degrees of freedom. That's because there's two variables. The one thing that might surprise us is the degrees of freedom for the SSY, right? Because those are supposed to be n-1. And what the kata, didn't we have 99 bears? That's true, right? Actually, what's going on in this particular instance is we added a variable, age, I think it is in this case, in which case we have some missing values. Apparently, it looks like we have golly, I guess 41 bears that we don't know the age of. And if we don't know their age, we can't use them in their model. So that is a little bit of a downside. Sometimes adding more variables means that, right, you're adding more missing values. And if any variable has a missing value, it can't be used in the regression model. So that entire observation gets thrown out. So in this particular example, right, we've added a variable which should kind of add more information, but it has come at a cost. It's not always the case, but in this case it is. We've almost reduced our sample size in half. So what's not necessarily obvious here, but you can hopefully take my word, and you have the bare data set, so again, you learn by doing. Might be worth exploring and validating the statement on your own. There should be 58 bears that have non-missing values for age. Or not 58, sorry, 57. So 57 minus 1 would give us the 56. And then you could remember that whole n minus k minus 1 thing for the degrees of freedom of the error, but I just remember that the numbers have to add up to each other. So if I know that I have 2 and I know the other one's 56 and that middle one has to be 54. Right, there are the sums of squares. All right, 648,964, so like 650,000. Looks like SSY is 820,000. 650,000 over 820,000 looks to be about 79%, right? That's our R squared. 650,000 divided by its degrees of freedom divided by 2 gives us about 325,000. 170,000 divided by 54 gives us that 3,151. 325,000 divided by 3,150, that's going to be, we can see, about 100, and actually it looks like it's exactly 102.98. And the p-value is less than 0.0001, so immeasurably small. We could actually build our prediction equation by looking at the parameter estimates, right? So the prediction equation is going to be y hat equals negative 312.76 plus 7.66 times length plus 1.00641 times age. For now, ignore the p-values in the parameter estimate section. They are probably not doing or not testing what you think they are. We will talk about what it is that they're testing next week. So for now, we should be comfortable with all of this output with the exception of the p-values and the parameter estimates. We'll talk about them next week. So here's what our hypothesized regression equation looks like. Y, the true weight of a bear, we're conjecturing is this linear combination of its length and its age. Our overall F-test had a test statistic of 102.98. This is an F statistic with 2 degrees of freedom in the numerator, 54 degrees of freedom in the denominator. Its p-value is less than 0.0001. Hence, at the 0.05 significance level, we reject the null hypothesis. What does it mean? Remember, in this class, so our p-value is less than 0.05. That means reject, but that's saying reject the null hypothesis is never an acceptable answer. What does that mean in the context of the problem? In the context of the problem, it means at least one of our two variables, right? At least one of age and length explain a significant amount of the variability in bear weight. Now, there is a follow-up question to this, a very important follow-up question, and that is, well, which one is it? Is age the important variable? Is length the important variable? Is perhaps both of them? Are they both important variables? The overall F-test does not answer that question, and as of this week, we will not have the ability to answer that question. However, we're going to spend all of next week talking about how we do that, right? The overall F-test is basically just telling us, is there nothing going on? In which case, none of the variables are useful. I can walk away. Or is there something going on? At least one of them is useful, in which case I need to dig deeper. Now, how do I dig deeper? That's what we're going to talk about next week. Here's the least squares regression equation. Y hat equals negative 312.8 plus 7.7 times length. And the coefficient for age was very close to 1, right? So 1 times x sub a. How do we interpret the slopes? We interpret it by saying, right, here I got both of them in the same slide. So interpreting the length, we would say for every 1 inch increase in a bear's length, we expect its weight to increase by 7.7 pounds. All other variables held constant. So in this case, assuming its age stays constant, which is maybe a more realistic thing is like if you had two different bears that were the same age, and one of them was an inch longer than the other, we would expect it to also weigh, right, 7.7 pounds more. We would interpret the age coefficient by basically saying, for every 1 year increase in age, we expect a bear's weight to increase by 1 pound, assuming its length stays constant. Okay. What weight would we predict for a 100-inch long bear with an age of 20? Just plug the numbers in. I'll leave it to you to pull out your calculator and verify, but I believe it's 477.2 pounds if we're using those numbers as I rounded them there. And if I want to do this in R, I just use the LM function. So LM is the linear models, is what it stands for. We sometimes refer to this regression model as a linear model. The y variable goes on left, just like in SAS. Instead of using an equal sign, R uses that tilde symbol, which is, yeah, it's right above the tab key, I think. And then you write as many variables as you want on the right, although in R we have to use the plus sign to connect them. All right, straightforward enough, hopefully. Not too bad, right? Let's do one last example to kind of reinforce this. New data set, believe a real life data set, a small portion of a larger real life data set. Looked at 60 houses, 60 homes. The goal was to find which variables were most important in predicting the sales price of a home. Which variables are most important in predicting the sales price of a home? All right, so here's the output. So you can see the 4 variables that I used. One is like square foot, so that's like the overall size of the house. How big is the living space in the house in square feet? One is the total number of rooms, the other is the total number of bedrooms, and the other is the age of the house. Okay? All those numbers should make sense to you. 4 degrees of freedom in the numerator because we have 4 variables in our model. Look at that ANOVA table. Look at how each number sort of beautifully flows from the other. Our p-value is immeasurably small, less than 0.0001, so that's less than the usual alpha level of 0.05. So at the 0.05 significance level, right, there is very strong evidence that at least one of these variables is useful in predicting the sales price of a home. You should be able to write the prediction equation. I actually leave it blank for you to write in yourself. I'm confident that you can do it on your own. And rather than me writing it and you looking at it, I would rather instead you write it and reinforce what we've learned today. We can look at things like age. Age has a negative coefficient. That makes sense, right? The older a house is, right, we expect there to be maybe more wear and tear, maybe a higher probability that it's going to need some repairs and need some extra money put into it. So the overall sales price might decline, right? A newer home in some way is flashier and perhaps more valuable than an older home. Although there certainly are some classics out there that might defy this rule. Yeah, so I'll leave it to you to write the hypothesized regression equation. We did it for the other one in a previous slide. All the difference is this one has 4 variables instead of 2. Don't forget the E. Here's the overall F statistic. I think I already kind of talked through all of this. Oh, I'm sorry. Looking at it now though, oh no, I think everything's fine. Yeah, I take it back. Yep. 4 and 55 degrees of freedom, p-value less than 0.001. So, right, at least one of our variables, at least one of our 4 variables explains a significant amount of the variability in sales price. I'll leave it to you to write down the prediction equation, the y-hat equation. And then for our last slide, I'll interpret one of our slopes, right? So let's look at the bedroom slope. The bedroom slope is negative 10.8. That makes sense, right? For every additional bedroom in a house, we expect the sales price, the units were in thousands of dollars, so we expect the sales price of the home to decrease by $10,800. That makes sense, right? Like, people are always saying like, ah, man, I really wish I can afford a house with just like 1 bedroom, but it's just out of my price range, so I'm gonna have to settle for a 10-bedroom house. Really not crazy about it, but you know, it's all I can afford. Right now, right, I could get my little starter home, just a small little 10-bedroom mansion. But whatever, years from now, I work hard, I hustle, get a few raises, maybe inherit some money. Maybe I can live the American dream of a 1-bedroom house. How nice would that be? I know. What the cutta? It seems unintuitive, doesn't it? Really, most of us think the opposite, right? That more bedrooms is better. And truth be told, I mean, if you look, I mean, you know, you may or may not have gone through, you know, buying your first home, second home, whatever. But I mean, if you do look, more bedrooms do translate to a higher cost, as we would expect. So what's going on here? Exactly, right? My interpretation is not entirely correct, right? Which is why we have to add that caveat. The caveat is, right, we expect it to decrease by $10,800, all other variables held constant, right? What are our other variables? Our other variables are the square footage of the house. Another variable is the number of rooms in the house, right? So, right, in this case, it's kind of like the slope it doesn't really have much of a useful interpretation because it doesn't really make sense for like bedrooms to be increasing while the other variables stay constant. Agreed? And that's kind of why we're seeing this decrease, because if the other variables are held constant, it's like we have the same number of rooms, but somehow are getting more and more and more bedrooms. So it's like every time we get a bedroom, it's like, oh man, I just lost a bathroom. Or every time we get a bedroom, it's like, whoop, there goes the living room, whoop, there goes the kitchen. Right? It becomes like a house of nothing but bedrooms. And of course, the size of the house is allegedly being held constant. So as we're adding rooms, right, we're not adding area to the house. We're just we're making every room now just becomes a little bit smaller to accommodate the new one. So we have a bunch of rooms, but no kitchen, no bathroom, and all the rooms that we have are these tiny little bedrooms that, right, barely have enough space for us to sleep in. So we have to be careful. This is what I was talking about, where like the interpretation becomes a little bit more complex, and we sometimes lose like interpretations, right? I mean, that negative 10.8, it's mathematically important. It's going to build us a good prediction equation, but interpreting it becomes, difficult. It doesn't necessarily have a nice interpretation anymore. That's a sacrifice that we've had to make to build this sort of larger, more complex model. All right. So that wraps up our third week. Should be some activities for you to work on, and I will see you in 7-ish days for Stat 512 week 4. Bye for now.